Hello everyone and welcome to today's lesson of Algorithms 1-on-1, which is a fundamental yet very interesting problem called merge two sorted arrays. As the input, we are given two sorted arrays and we will name them nums1, which is of length n, and nums2, which is of length m, and we should return a sorted array of length n plus m containing all elements from nums1 and nums2. For example, if we are given these two arrays, nums1 and nums2, which you can see that are both sorted, we are going to return this array nums. It contains all the elements from nums1 and nums2 and is also sorted. Alright, now that we know what the problem asks for, let's see the most naive approach. It is pretty simple, you might have already thought of it, and it consists of two steps. Step number 1 is to have an extra array nums in which we are going to push every element from nums1 and then push every element from nums2. And then, the second step, we just sort this array nums. What do you think is the time complexity of this algorithm? Well, the first step is big O of n plus m, because we just iterate through every element from nums1 and then through every element from nums2. And then we are sorting an array of length n plus m, which takes big O of n plus m crossed log of n plus m. So the final time complexity of this algorithm is big O of n plus m crossed log of n plus m. Pretty simple, right? Yeah. Well, this is not the optimal time complexity that we can achieve. The optimal time complexity is big O of n plus m. So let's find out together how the optimal approach really works. Let's take again the arrays nums1 and nums2 from the previous example input. We are going to need an array nums of length 12, which is initially empty. The first thing that we can do is ask ourselves what should be the first element in the array nums. Of course, this element could either be part of nums1 or part of nums2. Let's suppose it is part of nums1. Could it be nums1 of 2? No. Remember, this is the smallest element in the array nums. So if it is part of nums1, it should also be the smallest element in nums1. And it couldn't be nums1 of 2 because there are other elements on the left of it which are less than or equal to it. So if the first element in nums is actually part of nums1, it could only be the first element. Now let's suppose this element is part of nums2. Could it be nums2 of 2? Again, no. Why is that? Because being the smallest element of nums and also being part of nums2 means that it should also be the smallest element in nums2. So if this element is really part of nums2, it could only be the first one. Perfect. That's a good observation. So all we know for now is that the first element in nums is either the first element in nums1 or the first element in nums2. Which one of them should we choose? Of course, the smallest one. Because 1 is less than 2, nums of 0 is going to be equal to 1, and now we have used the first element in nums1. Okay, it's time to ask ourselves another question. What would be the second element in nums? It is either part of nums1 or part of nums2. Let's suppose it's part of nums1. Could it be nums1 of 2? Again, no. Because if this would be the second smallest element in nums, then every element on its left, which is less than or equal to this element, is going to be placed after it in the array nums, which is not correct. So if this element is part of nums1, it surely should be the first available element to use, which is not nums1 of 0 anymore, because we have already used that element, but is nums1 of 1. Following the same line of reasoning, if this element is part of nums2, it could only be the smallest available one, which is nums2 of 0. So we have again two possible candidates, and we should choose the smallest one, which is 2. Nums of 1 is 2, and now we have also used the first element in nums2. So we should increment the purple pointer, and now 4 is the possible candidate to be the next element from nums2. From nums1, the candidate is still 3. 3 is less than 4, So nums of 2 is equal to 3. We have used this element, so the green pointer is going to be incremented. 4 is less than 5, so nums of 3 equals 4. We have used the element, so we increment the purple pointer. 5 is less than 6, so the next element is 5. We have used it, and we will increment the green pointer. Now, 6 equals 6. So nums of 5 equals 6. But the question is, which one of them should we choose? It doesn't really matter. It is the same outcome. So let's choose the one from nums 2 and increment the purple pointer. 6 is less than 9, so now we will use the 6 from nums of 1 and increment the green pointer. 8 is the next element, increment the green pointer. 9 is less than 10, increment the purple pointer. 10 is less than 12, so the next element is 10 and we increment the green pointer. 12 equals 12, so it doesn't really matter. Let's say we pick nums 1 of 6, so the next element is 12 and we increment the green pointer. And finally, because all the elements from nums 1 have been processed, we will just push all the remaining elements from nums 2. And the only remaining one is 12. Now every element from both arrays has been processed, so we finish. All that is left to do is analyze the time and memory complexities of this algorithm. For the time complexity, we should notice that each element from nums 1 is visited exactly once, and each element from nums 2 is also visited exactly once. This means that our algorithm performs exactly n plus m iterations, and on each iteration we perform one comparison to see each candidate is smaller and one assignation to put the element on its place and increment the pointer. Both of these are performed in constant time, so the final time complexity of the algorithm is big O of n plus m. And because we are using an extra array of length n plus m to store the output, the memory complexity of the algorithm is also big O of n plus m. And that's all. Now I'll let you implement it in the coding tutorials. Have fun!